and I can do the downloading.
Okay.
All right. So there are two things here: configuration spaces and arithmetic statistics. This is a topology seminar, so I will focus on the second thing. Because we all know what the configuration spaces are, hopefully, or not. But okay. Just aside, the theme for today's talk is going to be about topological methods in arithmetic statistics. In particular, the overarching program that we're pursuing is to transform statistical questions. Let me take this one. In number theory into homological computations of spaces with coefficients in local systems. And this is a very kind of, this is a youngish, but also pretty standard program to this point. It started around, I guess, 2009 is the first breakthrough paper, which I'll get to. But here are some of the main tools that's in this program. The first one is Rothenlick-Lefschetz trace formula with twisted coefficients. This is the best introduction for me is from a paper of Schoch-Allenberg in 14. The basic idea is that it tells you, it gives a tool to translate counting functions into looking at like homological, in particular, eta cohomology of spaces. So if you have X, here, this guy here, to be a smooth projective varieties defined over a finite field FQ, then the action of Frobenius will fix any point, any FQ point on X, and in particular, it acts on the stock of the local system L at the point X. So you can talk about the trace of Frobenius at that point on the stock at that point. And what the Rothenlick-Lefschetz trace formula tells you is that if you take this sum over all X or FQ points in X, then the sum of the trace of Frobenius on the stock of local system can be computed by an alternating sum of the trace of the geometric Frobenius on eta cohomology. So all of these sounds very like a little bit more arithmetic, but the bottom line is that you get something not correct. All right, you get something more.
You should admit. Maybe.
I think it's Maru should do that.
Maru can do this, right?
Yeah. So what you can do, what it allows you to do here is that you translate something arithmetic into something more topological. That's the eta cohomology. So if you can get your hands on to eta cohomology of these spaces, then you can do something about arithmetic. Then the other two tools is the Deline's bounds on the eigenvalues of the geometric Frobenius. And the reason this is very useful is that in general, it's very hard to compute the action of Frobenius. So Deline's bound gives you like a gigantic like overarching bounds for what it should be. Basically, what it tells you is that instead of looking at the action, you just care about the dimension of the cohomology. And that's where Alton's comparison theorem comes about, when you can translate from eta cohomology into cellular ordinary cohomology. And that's where you can do all the topology you want, instead of having to deal with like, eta cohomology theorem, which is a little bit more difficult. Okay, so the bottom line is, with given this kind of standard machinery, what you do is that if you can encode your arithmetic quantity as a trace of Frobenius on a certain local system, then you can pass through the whole thing here and produce something like homology, and then turn it into a question about homology of certain spaces. Albeit with local system, but you can do that. All right, and like I said at the beginning, our main character for today is configuration spaces. I'll start a little bit back with like not a very traditional kind of definition of it, but a little bit more arithmetically motivated. So we find const n to be the space of monic square-free degree n polynomials. And so when you take it over C, then we recover our normal configurations, like our standard definition of configuration space of endpoints in C, which is the space of unordered sets of n distinct points on the plane. The way you can think about this is that, well, here for every polynomial that is monic and square-free, a degree n, if you look at the roots of it over C, then you indeed have n distinct points on the plane. Okay, so that's how you the C points of these const n looks like. Right, and it's well known that configuration space is K pi 1 of something called the break group, and this is like a very pretty well-known group that has the following presentation. So it has The group Bn has n minus 1 generators. Each of them looks like this. So that's like when you have the strands cross each other. And then it satisfies two relations. It commutes if they're far apart, and they satisfy a break relation if they're like next to each other. All right. So then the theme of, like I said at the title, the talk is about configuration spaces and applications in arithmetic statistics, and in particular, I would hope to describe application to two problems in arithmetic statistics. So the first one is what I will tell you a solution, and the second one is that I'm going to tell you about an upcoming solution. Okay, so this is the one that we already know what is going on. This is about character sums of something called the resultant. And this is a very classical definition in number theory. And is that, so given two monic polynomials f and g of degrees n and m, the resultant denoted by rest fg is a polynomial in the coefficients of f and g. And it can be computed by taking the determinant of their Sylvester matrix. I'm not going to write that matrix out, but it basically has all the coefficients of f and g in there. And in particular, there are a few, the most kind of amazing thing about the resultant is that it's this defining property is that the resultant is zero whenever f and g share a common root. And this is really like the first kind of application of the resultant where it came alive. And if you look at, then the resultant also has a formula given by the product of differences of the roots of two polynomials. So here you can see that lambda is taken from the roots of f, and mu is taken from the root of g. You take the products of all of those differences. And this can be taken over any algebraically closed extension of the base field K. And most importantly, as I said, it's like a determinant of a matrix that has just a bunch of coefficients. So it has integer coefficients, as you know, in terms of the variables of the coefficients f and g. Okay, and that's when you can take it over fq. All right. So our question that we're concerned with is that over a finite field fq, what can we say about this sum f chi nmq that's given? It's written on the right hand side here. The sum over polynomials f and g that are monic square-free polynomials of degree n and m. And we're summing over chi rest fg, where chi here is a non-trivial character of order d. So that is a homomorphism from the multiplicative group of fq to c. All right. So this is like a pretty kind of standard exponential sum that people usually consider in number theory. And well, I mean, then that's our question is like to kind of understand this. And one thing I want to note is that we can also insert the co-prime here without losing anything, precisely because the result is zero when they are not co-prime. So this sum here is the same as when we insert the co-prime. So this sum is first considered by, I guess this question is first considered by Ellenberg and Schusterman for the case when chi is quadratic. And in this talk, we consider really like any non-trivial character. And one thing you can kind of imagine this character chi rest here is that it's similar to the residue in the residue symbols for integers. So for integers, you know, like the most famous residue symbol is the Legendre symbol that detects quadratic residues. And it's kind of like the resultant is kind of like a similar way of doing that for polynomials. So it somehow kind of detect like the arithmetic properties of pairs of polynomials. All right, so that is the problem, and it turns out that we can approach this from topology. Surprise, surprise. And in particular, our main topological thing here is the bicolor configuration spaces. So again, I'll start with a little bit more arithmetic kind of way, a way of defining this. So define conv nm to be the space of pairs of monic square-free co-prime polynomials of degrees n and m. Notice the co-prime. So because they are co-prime, then when you take the C points of this, you obtain something that's pretty that's a little bit more easier to understand in like, you know, topologically. As the space of unrest sets of n blue points and n red points are distinct in C. Again, it's because they are co-prime and each one of them is square free, and you get all these points separate. Okay. And so there are a few facts about this. Well, because they are all separate, because the polynomials are co-prime, then you see that the resultant lies, this space lies inside the resultant locus. That means it restricts to a map that avoids zero. And in particular, const nm of C is in fact a k pi one for something called a mixed break group, which can be defined kind of two ways. The mathematical way of defining this is that you have a projections from B and M to Sn plus M by just looking at the endpoints. And then there's an inclusion of the S of Sn cross Sm in Sn plus M. So the mixed break group B and M is precisely the pre-image of Sn cross Sm under this map. And so that's the mathematical way to define this. But my preferred or my favorite definition is a pictorial way of defining it. It consists of all of these breaks on the right-hand side that has, well, blue strands and red strands, and it has like a partition on the endpoints. You let the strands kind of go and mingle each other, but then it has to return to their own partitions. They don't have to go to like the same point because that will be the pure break group, but they have to kind of, again, preserve the partitions on the endpoints.
Wait, I'm not
yes.
sure what you mean. Could you explain that again?
Yes. So for example, here n is 2 and m is 3. That's 2 and 3. So this is like a break that you can like the break that the strands start from this partition of the endpoints. They can go around, mingle with the one in the red, but then they have to return to the same partition. So it's like you can see there's a cutoff here in terms of the like endpoints. Okay, so you don't just concatenate the two breaks together. That's different. Now you let them, kind of cycling around in the space, but then they have to return.
Oh, I see. Thank you.
Okay, any other questions? All right. So in particular, because of the way we describe it, you can pretty easily see that there are three kinds of generators. It's the one that's the standard generator, blue and blue, red and red, and there's the one that sits right in the middle of the two partitions that let you go blue around red and back on the right hand side here. Okay, so we can define like a representation. For example, here's a one-dimensional representation over C of the mixed break group B and M that defines by when you send the standard break generators of blue, blue, red, red to 1, trivially, and then the generator that's called a mixed generator is going to act by multiplication by a root of the D root of unity instead of D. Okay, and then I like the script L to be the associated local system on const nm. So what is the upshot of this? Well, why do we care about this local system? It turns out that, and this is observed by algebraic Schusterman for the quadratic case, and I generalize it for all characters, is that the trace of Frobenius on the stock of this local system at any point fg, here the point, remember the space is const nm, so the point is denoted by a pair of polynomials fg, and the trace Frobenius on the local system is actually given by this chi-res fg. Okay, which is exactly what we are trying to count. So the upshot of this is that we can rewrite our sum as the sum of all points in const nm of fq, summing over and summing the trace of Frobenius of elements on the stock of the local systems. But then by the Grothendieck-Lefschetz trace formula I mentioned before, we can write this as the alternating sum of the trace of Frobenius on étale cohomology of this space. So now what we have turned is that we have turned the statistics about this sum f chi into the statistic about the homology of these mixed break group with this particular one-dimensional representation. Now this is not a trivial representation. So that's what makes it difficult, is that, well, we know all about the break groups, homology of break groups, with trivial coefficients from Pratt-Cohen, Arnold, they have Boston-Worth. It's been like from the 70s, but the twisted coefficients is a different animal. But that's we will hopefully approach it. And so here's some of the main results. So what we prove is that the ith homology of the Bn and with this coefficient, it vanishes for all I less or equal to max and m minus 2. So this is proof for when one of them is 1 in my, if you remember from my last talk from last like year, and I you know,
One of them in an N or M.
yes, yes. If one of them is 1, then we prove that, and then, well, I talked about last year, and then, so now this year, the new thing is that, got it for ONN. All right, so,
Is it for an arbitrary local system and what kind of conditions?
no, this is only for that particular local system that we have there.
Oh,
Yeah, the one-dimensional one. Yeah,
Where does the D come from? You're
Where does
taking a
the D-
root of unity.
yeah, the D comes from the order of the character.
Okay.
Yeah, because you think about the character, so basically, if you look at the resultant map over C, it basically counts the number the winding number of that elements here. So you count the number of red and blues mixed together, and then what the character does is that it basically asks you whether, you know, what, like you basically send, so that's the map Z, right? It's a map to Z, and then the character just send you from the map to Z to Z mod D minus 1.
Does the D tie up with anything else? Like you've got this D root of unity. Is there anywhere else in what you've said where D appears?
Yeah, so,
Aside from the fact you've got a theorem about this particular D, but
yes.
what else does it connect with?
Yes, so, okay, so I guess number theoretically, that's where the D comes from. Topologically,
So where does it come from, number theoretically?
it just from, let me go back all the way, well, that's hard. So there's a okay, yeah, so this comes from like the sum we consider.
But
Right.
the D could be arbitrary.
Oh,
Like
yes,
it's,
yes.
well, yes, but.
Well, I guess you have to
there's
be,
no connection that this D is specified by anything else. It's just that for every D you have this result.
that's right, that's right. I think for, in particular, when D is 2, that's a quadratic character, and I think that's the original reason why they look at it, is that it has something to do with certain, it appears in some of the studies of Will Sawin and Mark Schusterman on like the twin prime conjectures for FQT for function fields. So they come up, these kind of characters comes up. That's why they were interested in it, and then, but yes, there's no restriction on D as far as long as the topological from the topological standpoint. Except for it does matter in the computation. Okay. Any other question? This is like freezing. Both me and my computer. All right, yes. Oh, I got ahead of myself. Okay, so then given this, you can do the same standard trick of arithmetic topology, and you can produce a bound of this sum that's given on the right-hand side. Well, let's not care about the 2 power here. That just comes from us being unable to compute all the cohomology. But the most important thing to look at is this minus max nm over 2 here. This factor here comes directly from this vanishing range. Okay, the basic idea is like you basically, given the vanishing range, you get rid of a bunch of terms in your sum, and that produce the upper bound on this sum f chi here. Okay, so one thing, getting back to Peter's questions, one thing I want to mention is that given D is 2, the computation for D is 2, and when D is greater or equal to 3 is a little bit different. They produce different cohomology a little bit. So in particular for D is, when D is not 2, then you can improve this to -1, but for when D is 2 is the -2. So there's like that difference in the computation. All right, but I just want to state it for all non-trivial characters here. Okay, and in particular, well, you can observe something like a very similar behavior for like residues, residue symbols of integers. Is that when you have a sufficiently large Q, then asymptotic average of this character of resultant approaches 0 whenever as you have like the degrees of 2 polynomials increasing. It can be, they can increase both at the same time, and you still have the same behavior because your vanishing range is in the max. It's the max idea. All right.
So what is the moral of the story? That asymptotically
Yeah.
polynomials start having common roots?
I think that's a little bit different, in this, right, so, let me think about this. So if you think, the easiest way to think about this is in the sense of like, if you take chi to be the quadratic character, then asymptotically, what it's saying is that you are having equidistributed of the resultant between -1 and 1, between like, being a square. In FQ,
It's not just the vanishing of the result, but
Yeah.
chi, the character.
Exactly. So you are like detecting, like you are detecting properties of the resultant of the two polynomials. Now, whether to say that what tells you about just the relationship between the two polynomials, and I'm not so sure how to get all the way there, but like people do look at like the resultant of f and g as like some like some important invariance of the two polynomials. Right, any other questions? Okay, so, well, all right, then let's say the proof strategy is to study the homology of these mixed break group with coefficients in a more general exponential representation of B and M. And now normally I'm done with my talk, right? So we can, if you, the rest of them you can zone out because it's gonna be technical and topological, so, yeah.
So I think last year when you were able to show the first theorem there with n equals 1,
Yes.
At some point you were like, my technique is like fundamentally stuck, like I need to approach it from a different way. Is that what you're about to show us?
All right, I guess I'm disappointing you if I were like remembering that, but so the technique is, okay, but
I could also be misremembering.
the technique is gonna be expanding last year's technique, unfortunately. But there are like a lot, there are some more combinatorics coming into it, and more and more punctures. Okay, so we get there. All right. So, okay, but so the framework we are getting from is in fact from another arithmetic statistic / topology paper, Ellenberg, and Westland, which I've talked about way too many times, and you probably get sick of it. But let's discuss some of the topology they did. So, but the bottom line is that they compute the homology of break group with certain twisted coefficients, and we will look to expand that for other kind of break groups, break generalization of break groups. Okay, so a braided vector space is a finite dimensional vector space V with the braiding from V tensor V to itself, such that it satisfy the braid relations here. And if you recall the presentation of the break group I showed you before, you can see that there's a matching between this braid relation required for the braiding and this braid relation in the definition of the break group. And so, in fact, there's a natural representation of the break group Bn on the n-fold tensor of V, defined by just having the map, the braiding sigma acting at the ith position in the tensor product. Okay. Now, given this representation, we can also define an algebra that's called the quantum shuffle algebra. And this is a braided graded bialgebra with the underlying coalgebra as a tensor coalgebra. So as vector spaces, it's just the direct sum of all of the tensor powers of V. And we're equipping this with a shuffle product. So what is this? What this does is that first, you have two things. I'm using the bar complex notation here. You got A1 for AN multiplied B1 for BN. What you do is that you first concatenate them together to get an element of V tensor N plus M. And then you're allowed to apply braid actions on that vector space. So what this does is that what you do is the multiplication will sum over all NM shuffle tiles. And then you have where you have like tau, the length of tau acting on this concatenation. So what is an NM shuffle? An NM shuffle is a permutation of n plus m points, such that I preserve the order on the n and the m parts. You can see like by these arrows. And then the lift we're using is basically lifting all of the strands from the right to left up and all the other one behind. So this is the standard lift of this shuffle, right? So we're summing over them for the product. And their main topological result is that they prove that there's an isomorphism between the homology of the break group with these v tensor n times coefficients and the x algebra and the x algebra of the over the quantum shuffle algebra A defined from some twisted dual of B. Okay. And when you know this, then maybe hopefully now, even though the quantum shuffle algebra is very complicated still, you may have a little bit more you have a little bit more tools from homological algebra to deal with it. Okay, now that you can write it as an extent. All right. So what we try to do is that we try to improve their or extend their theorem to some other scenarios. But let's start with like the way they kind of go around and prove this. So their proof rely on something called the Fox-Neuwirth cellular stratification of configuration spaces. And so here, if I start with Con and C, what you can do is that basically the cells in this stratifications is by putting points in columns. That's what I usually like to say. So here on the picture, there are 17 points. And this cell here is defined by putting points into columns according to a particular partitions. So the index of the cells in this stratification is by order partitions of n. Here you see 2, 3 points, 4 points, 5, 3. So this cell here, this is the configuration in the cell denoted indexed by the partition 2, 3, 4, 5, 3. Okay. And the boundary cells are obtained by a few ways. You can either send a point to infinity or collide the point together. Well, we don't want to do that because we want to keep the number of points fixed in our configurations. So what we do is that we just send it to the point infinity. And in particular, this stratification gives you a CW complex for the one-point compactification of configuration space. Yeah, that's why we need the point infinity for. Another way to obtain, yes.
I think also boundary cells are obtained by merging the vertical lines together.
Yeah, I was going to talk about it. So that's the second way you want to do that. And that's the right way. Is that otherwise it's like a what like a trivial stratification. I mean, look, we have like a zero differential if we were just sending everything to zero. Yeah, all right. But the right way to obtain a boundary cell in this stratification is by joining the columns together. So what you do is that you look at two columns, you sum them up, right? You just collide them together. And in terms of dimension, you see we lose one column. So we lost one dimension. Okay, that's good. That means we're looking at like a boundary cell. Now, when you join the two columns together, notice that they're all these points on their own column. You cannot pass them through each other. So their order are fixed. But then you can mingle them together. You can choose to send where these 4 points go between these 5 points. And that is defined, that's governed precisely by a shuffle, right? It's where you have two sets of points and you kind of mix them up. Okay, so that's where the shuffle comes about in the structure of the stratification. And so if we kind of decorate it with something, what if we look at local systems? So here, the way I like to think about this is that if you look at the representation of Bn on the n-pole tensor of a braided vector space V, you can kind of think about it as like decorating each of the point with a copy of V. Okay, if you were to do that and observe that each of the columns, you have like certain number of copies of V. So the first one is V tensor 2 twice. The next one is V tensor 3 times, and so on. Okay, and each one of these, though, in turn lies inside of, it's like an element of the quantum shuffle algebra. Remember, we talked about the twisted dual. It's like kind of like some technical stuff. So let's just think of them as just like plain braided vector space V. Okay, but each one of these columns then can be represented somehow by a copy of the algebra. And when you look at, for example, here you have 5 columns, then in turn you can see that this is like this is basically the bar complex. It lies inside the bar complex of the algebra, right? When you have the bar complex is where you have a bunch of copies of algebra tensor each other. And then, so that's their vector spaces. And you look at the differential. Well, what does the differential do here? Differential do by colliding the 2 points. And in particular, now we have these, so we have to use the multiplication structure inside the algebra. And that basically mesh with the differential of the bar complex when you multiply the two consecutive elements.
And,
Yeah.
Please remind me, what is J2?
Sorry, this is I, and this is, so these are the augmentation ideals of the algebra. Basically, we are saying that we don't have an empty column. Yeah,
I see.
yeah, just that. All right. Any questions so far? So I hopefully convinced you that this tells you, okay, this is like saying that the compacted homology of configuration space with this local system equates the homology of the bar complex, which is Tor. So you can do some dualization and get their theorem. Okay. And what I would like to do is that I would like to basically produce the same picture, but with punctures. Is the punchline. And last year I did one puncture. This time I had a bunch. All right, so we get there. Okay, but first let's kind of set it up a little bit more precisely what we're looking for. So we're looking at like two colors, right? We're looking at the mixed breakgroups. There are two colors, and in particular, they should be decorated by two different kind of braided vector spaces. So let V and W to be two braided vector spaces with a mixed braiding tall from V tensor V tensor W to itself, satisfying some compatibility conditions. So basically you want them to give a nice representation of the mixed breakgroup on the tensor V tensor n times tensor W tensor n times. Okay, and I let the script out again to be the associated local system on the space. So the goal now then is to study the homology of configuration space of n blue points and n red points on C with this particular twisted coefficient. So you can see this is this is like a more general kind of coefficient than the one-dimensional thing that I talk about. But in particular, when in our application, it will specify onto the one-dimensional case. Okay, but I mean, we'll get to it, but this is like definitely a more powerful kind of setup. All right, so the approach we're taking here is that we are not studying this space on its own, but rather we will use a fibration of Fadel-Neuwirth that basically you can look at is that there's a projection from the bicolor configuration space to the normal configuration space by forgetting the blue points. And the fiber of that is the configuration space of n blue points with n punctures. Okay. And so what you can do then is that this induces a spectral sequences that computes the homology of the mixed configuration space, the bicolor configuration space, from the homology of the configuration space with coefficient in this homology. And our goal would be to actually compute the homology of the configuration space of puncture planes instead. Okay. And so as you can, to sorry disappoint Trevor, but then we kind of did like C m equal 1 here last time, and I'm going to try to do m for arbitrary m's. Okay, so what is the difference? Well, the difference is we put more punctures on it. So what happens when we put punctures? Let's say we can just put the punctures on maybe like add all the integers, non-negative integers on the real line. And it changes the stratification a little bit. What it does is that we will have some columns that has punctures which cannot move horizontally, and we don't allow the points on the columns to pass through the punctures. So in particular, the number of points that has negative imaginary parts on these columns has to stay fixed. So those are the new kind of information in our stratification. And it does form a stratification, trust me. Now, if I were to decorate it with the representation of tensor powers of V and W's like we're meaning to, well, we decorate all the points with a V and all the punctures with a W. Okay, and heuristically, what you think about this is that again, each of the columns that doesn't have a puncture is still something in the quantum shuffle algebra, but every column that has a single puncture, this is the key point, is that we have a single puncture. We make a choice to spread out the punctures so that on every column that has a puncture, there's only a single one, and that means that kind of gives me a module structure on this. So basically, this module over the quantum Shopper algebra is the same as the algebra, except for I input a W everywhere. And every summand has a single W in there. And the multiplication kind of moves your W around as you expect. Okay, but if you look at this now, then this is very close to the form of the bar complex. But if I have a single module, for example, this is very close to the Hausdorff chain complex, right? Where you have a single module and then you have a bunch of algebras. Okay, so the proof of this theorem here kind of goes through constructing a kind of multi-module Hausdorff chain complex, and then you use like you construct like an n simplicial object that converges to that totalizes to the cellular chain complex of this guy. Okay. That's why in this main theorem you can see there's an iterated derived tensor product. Okay, but the main theorem is that I have the homology of the one point of rectification of const and Cn relative to the point infinity with these twisted coefficient. There's a dual. It's kind of correspond to what it's technical, but that matter. But I can compute this as an iterated derived tensor product of these modules M. And there's like an overarching tensor over the enveloping algebra with K on the front. So what I like to think about is that the guys here in the middle, the tensor product over A, those are describing between the two columns. All right, so between two columns, you can see there are a bunch of copies of the algebra. So if you isolate two columns, that's like a bar complex of the two modules. That makes sense? Okay. And then, so that's like this part here. And then this tensor over A, tensor A off, that's like a Hausdorff chain like that's like a Hausdorff structure that somehow describe like a wrapping around the whole space from your first column to the last column. Okay, there's like some shifting degrees and total degrees, but the gist of it is that you can compute this by looking at like some iterated derived tensor product of these modules. Any question about this general theorem?
What would be harder to compute, the right hand side or the left hand side?
Yeah, exactly, right?
I was about to ask, like, how computable do you feel that this will be?
Yeah, so surprisingly, even in the case where there's no puncture, even in the original Alan Richard Wesseling paper, they didn't compute a thing. They somehow get a very bad bounce by 5 different very bad bounds that's turned out to give you enough. It's bad enough that it gives a good thing.
But they were working with the left hand side. So
They actually work with the right hand side.
the right hand side.
So they move from the left hand side to the right hand side, and they can use whatever homological algebra they can do to bound the cohomology of the algebra. So and then that in turn gives you a bound on the homology of the configuration space. So that's the kind of the key idea is like, I mean, I think their paper is like what now the revised version is like 80 pages, and then it's like 50 pages onto just bounding the cohomology of the algebra. Yeah, the topology is only 10 pages, which is like that, which makes me lame, but doesn't matter.
What do you mean by like bounding cohomology? Like,
Yeah, so remember the main theorem they have is like on one side they have like homology of break groups. Right hand side they have X of the algebra A. So what bounding is like they compute they give a bound on the dimension of the cohomology of that cohomology of the X. Okay. So that's what we will hope to do towards the end of the talk. Well, hope to do. That's what I hope to do, and I will tell about it towards the end of the talk. All right. But let's do what we can do first. Is that we can apply this to our first problem. It's about character sums of the resultant. So when you take these vector spaces V and W to be just C, and then your the bratings are going to be given by multiplication by certain units. In particular here, the standard brating is given by U, and then the mixed brating is given by the tau. Tau is given by P. Then when you specify U to 1 and P to zeta D, which is a D root of unity, this recovers the one-dimensional representation of mixed break group that we discussed at the beginning of the talk. And in this case, well, it's actually pretty computable. Because we have a description of the algebra given by Caligaro. It's called the quantum divided power algebra. And we show that the module M is in fact a free left or right A module. Okay, so because that is free, all the left derived tensor is gone. We just have to look at the actual tensor product. Okay, so what we do is that we can compute homology, the configuration space endpoints on puncture planes with these coefficients. And interestingly, the results divided into certain cases, depending on whether minus u is a primitive root of unity and whether p is the power of minus u or not. So you kind of have like 4 different cases with these guys. And so the main theorem, I guess, well, corollary of the main theorem, which is the theorem, is that in this case, the homology of configuration space on the NCM vanishes for I smaller or equal to n minus 2. And if you remember, we can use the Fadder-Newworth fiber sequence to obtain a vanishing range on con NM, because that's a little bit different because there's the max NM here. The max NM comes from the fact that the representation is symmetric between n and m. So in particular, you can choose either m or n at this, at this point, and then your result gives you a bound here. Okay, so that proves the main topological theorem or result statement that came into our bounds of the result, the sum of the resultant earlier. So we are done with, well, not done, but we have done what we can do with the first problem at this point. Okay. All right, I see I have like maybe 6 more minutes. Any question about this before I'm gonna kill us with like a rant for 3 slides? Good. All right, so if you have known Craig's work, then you know that his paper is not just about homology of configuration spaces. It's about something called the Mahler's conjecture. Yes. And this started with a very famous problem, the inverse Galois problem. If we should ask, does every finite group G appear some Galois group of some number field K? And there are a lot of frameworks proposed for this, but there's like governing one by Mahler. If we let NDGKX to be the number of degree D extensions, sorry, this is a different D, of L of K with discriminant less than X in Galois group G's, those are something that specify your equal extension, then this number kind of grows asymptotically linear, like polynomially in X with some like power, specified power by only depending on the group A. And then you also give like a more precise conjecture saying that is asymptotically something like C times A X to the A times the log X to the B minus 1. So there's like a log factor that's in the strong, that's called the strong Mahler's conjecture. Okay, so those are some governing principle that people in number theory care about and try to prove. And this has seen some computations. So what do we know so far? Well, the case when G is abelian is proved by Wright in 89. For G for S3, Davenport and High-Brown, Dakovsky, Wright proved it in 70s, 80s. Kluner gave a proof for G is a generalized quaternion group, but also give a counterexample for the strong conjecture. So the constant that Mahler gave B is not exactly precise, and then Turkelly give a modification in the conjecture that incorporates all of the known results. So it accommodates Kluner's counterexample. And then more recently, Bhargava and Shankar and Wang proved it for G for S4 and S3, those symmetry groups. And one thing I should have mentioned is that all of the things we talk about, it applies equally well for number of fields, which are finite extensions of Q, but also apply for function fields, which are finite extension of the field rational functions FQT. Okay, and so when we look at that, then we have a few more results by Oliver, Venkatesh, and Wesley 16 in the case of function field. And for G's generalized area group of order time to Q, and most recently, Albrecht and Wesleyan, well, should have been 17, but then they insist to put 23 because you just fix it now. Prove that the upper bound of the weak Mahler conjecture for for function fields for all choices of G and sufficiently large Q. So this is the kind of the key improvement here is that now that they look at just the function field case, they can really widen their wish for all Galois group Gs. Okay. And why care about this? Well, because there's cracks in both of these papers, you might expect that they use topological methods. And that's why we started there. So, okay. So let's see. I'll make it. Okay, so let's talk a little bit about their outline, how they approach the problem. And like what I promised is that the topology we talk about is going to play a role here, not a minor role. So if we fix a transitive G, a group G, that's a subgroup of the symmetric group SD, and a conjugate C invariant set C of G, then the first thing they do is that they relate this number that we talk about, but now they kind of also specify something called local monodromies, just well, it's like some additional kind of structure, but it does recover their original count when you take C to be almost all of the group G. Okay, so they study something a little bit more general than the modern conjecture questions, but it turns out it's a little bit easier to approach from a topological standpoint. Okay, so they relate this number to the Hurwitz space parameterized branch covers of A1 with n branch points, Galois group G and local monodromies in C. So basically, like in this case, they also use the same kind of standard machinery we talk about, where you start with like kind of point counting over something called the Hurwitz schemes, and then you pass through a series of spaces up to this point. So I'm not going to go into that, but the basic idea is like they also use the same standard machinery, just a little bit more complicated arithmetic geometry. All right, but after we use that, we look at the homology of these spaces. Basically, is the idea. Then what they do is that they identify the homology of this Hurwitz space with the homology of the break group with coefficients in V tensor n times, where we take V to be the braided vector space spans by this conjugate C invariant set C. Okay, and the action, as you can see here, the Hurwitz action when you send G tensor H to H tensor G conjugated by H. I think that's like a pretty common thing in combinatorics. I think like the Hurwitz action is what they call it. But I've seen it once or twice. Okay. All right, now comes the part that we talk about. Okay, now we have translated our problem into homology of break groups, and step 3 is in fact the step we talked about where they identify the homology of break group with cohomology of the algebra, the quantum shop algebra, and last step is when they bound the cohomology of the algebra. Okay. And in like the cohomology algebra is like the bounds exponential in Q and polynomial in N basically. So it's a pretty bad bound, but bad enough for them to say something meaningful about this. Okay. All right, so I'm going a little bit over time. Let me wrap it up with what is the work in progress about something I call the modulus conjecture with prescribed ramification. So the bottom, the thing we want to study is the number of field extensions of FQT, again, in the function field setting, with prescribed ramification at a finite number of primes. Then this number can be related to a Hurwitz space over a base curve with punctures, where you can think of like the punctures as the places where we specify ramifications. So the monodromies around the punctures are encoding the ramifications that we want to specify. Then, in particular, the idea is that they can be encoded topologically, like algebraically, by these conjugates invariant sets C and C prime, and then we can define braided vector space from those, similar to the way that Allenberg, Chen, and Westland did it. Then the homology of configuration space with of points on puncture planes, well, with certain twisted coefficients, with these twisted coefficients coming from these braided vector space we talk about, those can compute the homology of this Hurwitz space. Okay. And what we did is that we related the homology of this homology of configuration space with the cohomology of A by modulus M. And very recently, I found a way to bound the cohomology of the module by leveraging the bound on the cohomology algebra that they give. So the idea is that, and the result is that they have the same bound. So they have the same growth, the cohomology of the modules and the cohomology of algebra has the same growth rate. And that strongly suggests that that strongly suggests that the upper bound in the Mars conjecture for the prescribed ramification case is the same. And that was actually predicted by something called the Mahler-Bergauer principle, that, there are like number of theorists kind of been developing. Okay. So yeah, I think that's probably where I want to stop. Here are a few references. Again, 2 papers are there, one is coming, hopefully. And then, yeah, thanks all for listening.